Hello people, my name is Josh. I was a computer science teacher for nearly a decade, and now I've been running a tutoring business for the last 5 years, helping thousands of students to get better grades in computer science related courses. I was also an examiner for AQA, OCR and Cambridge International, and what I've been trying to do is put a series of lessons together to help you out in areas which I see all of my students getting wrong so that you can get better marks in your grades. And one of the areas that I've been looking at is logic gates with my students, and they've been really struggling with these. Boolean algebra relates into this as well. So I was going to do a lesson on logic gates and then move into Boolean algebra. And then also with OCR, I was going to do a separate lesson because they use a slightly different style of Boolean algebra that AQA and Cambridge International don't do. So if you're doing the OCR specification, just go on to that video. What we need to do is we need to just make sure that we actually understand what the different logic gates do, what the Boolean algebra related to it is, and then also the truth tables for each of those. After this lesson, what I'll do is I'll then do a lesson on Boolean algebra so that then you can look at how to simplify and work with those ones. So let's have a look at this one. Logic gates, the ones you've got to know are not, and, or, XOR, NAND, NOR. You need to be able to draw each of these. So you need to be able, so in your notes, what I would do is I'd put a section for NOT gates. I'd put that the key thing with a NOT gate is that it only takes one input and then it goes into an output. So you've only got one input and then it goes into one output. This is different from the other ones which take two inputs and give you one output. What a NOT gate essentially does is it reverses what you put in there. So if it's a 0, then the output becomes a 1. If the input is a 1, it then becomes a 0. The Boolean notation down at the bottom here, as you can see, is if you wanted to put a NOT gate, you put the letter and then you put a line above the top of it. If you want to sign up for free exam support, please click the link in the description and remember to subscribe for more free content. We're then going to go on to an AND gate. An AND gate, way I remember what an AND gate looks like is it's kind of like the D at the end of AND, if it was all capitalized. So if you go A, N, and then you've got the D there. So with the outputs on this one, an AND gate is only true when both you have two ones going into it. So you've got one going into A, one going into B. And then that gives you the output of a 1 overall. The rest of them, for any other set of inputs, then that is going to give you a 0. The Boolean notation for this one is you put a dot. It's like the multiplication sign. So you just put a dot there, and that is how you would write AND in there. Or the way in which I remember to write OR is imagine, because the back of it's curved, imagine that you would draw the O in there. You should be able to draw the O in the OR gate. So you've got it going like that. The OR gate works if one or the other or both of them together. So as you can see, the outputs are going to be 0, 1, 1, 1. And then the Boolean notation for this is just a plus sign. So one or the other or both of them is the way to remember this one. Now going into some of the gates which are you won't have seen in any of the GCSE courses. The XOR gate is what's called exclusive OR. So some people call it XOR, some people call it XOR. How it works on this one, so it's the same as an OR gate. You just draw a little line at the back of it. If you miss the line out, obviously you will not get the mark for it, so make sure that you do that. And the output for this one is it's exclusively OR. So it's not when both of them together. Comparing that to the OR gate, where you've got both of them, so it's one or the other or both. This one is just one or the other. So it's, if you were to say, if you were exclusive, if you were in a relationship with someone and you're saying that you're exclusive with them, that means that you are just with them. So it means here you've got 0 or 1. So it's exclusively OR. It's not both of them at the same time. So that's the way of thinking about that one, and that's how the truth table works. The Boolean notation for this one, so it's the plus, but you just draw a circle around it. NAND is where is essentially not and. So one of the things with the NOT gate, you'll see at the start, it's got a little circle on it. Now, if you miss the little circle, I should make a note of, if you miss the circle out and you just draw the triangle, you won't get the mark in the exam. So make sure that you write that down. The NAND gate is essentially the little circle is the thing like converts it into a NOT. Think about it like that. So it's not and. Whatever and was, which is where we've only got a 1 there, a NAND gate works in this way here, so that you've just got the ones. You've got the ones for where it was 0 in the AND. The Boolean notation for this one, so A and B, and then you just draw a line over the top of it, signifying that it's not. A NOR gate, which is just not OR. So again, it's exactly the same as an OR gate, but you just draw a little circle at the front of it. This essentially puts it through just knots everything. So if you imagine an OR gate, the truth table for it, 0, 1, 1, 1. This one here is going to be 1, 0, 0, 0. So it's just the reverse of it. And again, very, very similar to the NAND gate. You're going to do A or B. And then you just draw a line over the top of it to show that it's knotted. Now, a sort of knowledge question that you may get on this one is talking about the idea of a universal gate. When you come to do more complicated logic gate questions, that if you go on to study this at university potentially, there's a lot of rules which are to do with how you can change whole logic circuits into just NAND gates. And it's this idea that a NAND gate can be used to represent pretty much any other logic gate pretty much any other logic gate that exists. And it's this idea that it's what's called the universal gate. Now, you're probably thinking, why is that important? The idea that if you use just NAND gates, it can actually really minimize production costs. It can make things a lot cheaper. You can also use fewer gates, which can speed up the processing, because if you've only got to program it for just the use of NAND gates, that is actually going to make it a lot better for processing. So those are the two. If it gives you a question where it asks you to simply describe this, then you've got that in there. Some of the things as well that they may ask you to do is combine certain gates together and work out what the output for this is going to be. With the output, this is how I would do it. If it gives you this is a relatively simple one, but essentially what they might do is might give you a more complex one. When you've got the truth table, what I would recommend doing is just put a letter after each of the gates. And then all you need to do is you just need to focus on that particular gate. Where I see people making lots of errors is where what they'll do is they'll try and do too much, and they'll try and work it all out, and then they're trying to hold too much information in their head. Just split it up. So here we're just going to focus on just this one. And what we do is then we can see that this is an AND gate. So if the inputs are that, we're going to put a 0 there. If the inputs are that, we're going to put a 0 there. And then we know with an AND gate, the only way that we get a 1 is where both of the inputs are going to be 1. After that, then what we've got is then we just take on then we've got the NOT gate. So we take the output of R and we put it through the NOT gate. So 0 turns into a 1. That 0 turns into a 1. That 1. And then finally we've got a 0 at the end there. And we can actually see that is a very, very similar, where it's exactly the same output for what a NAND gate would be. Essentially, a NAND gate is a combination of an AND gate and a NOT gate, but we've just simplified it into just one gate here. Now, when you're going through this, you can obviously increase the number of inputs. You're going to get some more complicated ones in your exam papers. And it's just, as I said, just about splitting it up. That's what I would be doing, is I would be making sure that I'd be writing in what the output is here and then focusing on just this section. Once I've got that one, then I would focus on this one. And here you can see the Boolean notation where you've got A and B. And then finally the input is going to go into there. So then it's going to be plus C there, because we're going to put the C in there, and then we're going to take the R, the output of A and B, which is R, and put it through that. And on this slide here, I've got an example of that. So you write down all of the potential inputs for the 3 examples. So you go working your way through. Then we just take R. So we focus on just this section here. So if we imagine that we're just going on A and B, so what is A and B? Don't even bother looking at C, because this is just for the R column. So 0 and B is going to give us 0. The only way that it's going to be a 1 after this is if we've got a 1 and a 1. So you can see here 1 and 1. So that's why we've got a 1 there. The rest of them are zeros, because 0 and 1 for an AND gate, that's going to give us an output of a 0. And then it goes all the way through until we get right to the end, which is a 1 there. We then, once we've done that column, then what we're going to do is then we take the R column and the C column, and then we're going to put it into an OR gate. So we go 0 or 0, which is 0. 1 or 0, which is 1. 0 or 0 is 0. And then 1 or 0 is going to be 1 because it's going through an OR gate, so it's one or the other or both of them. If we've got two 1s, that is also going to be a 1. So that's going to be taking you through generally the basics that you need to understand for logic gates. So the 6 gates that you need to know and how to combine certain logic gates. In the next lesson, what we'll be doing is we'll be having a look at Boolean algebra and how we can actually simplify some of these expressions to make it more easier and more efficient to look at. Thanks for listening, people. If you want to sign up for free exam support, please click the link in the description and remember to subscribe for more free content.